Hey friends, this is Visionary 3D, and today we're going to make JavaScript 16 million times faster. JavaScript is a slow language, isn't it? It's not built to make games or any kind of complex math-heavy application. So how can we make our web applications fast when the scripting language that we're supposed to use is so goddamn slow? In this video, I'm going to show you 3 game-changing techniques which you can use to make any web application fast, and in some cases, blazingly fast. 1 year ago, I really couldn't make this video because the technology that I'm going to show you today didn't exist. You know what I'm talking about. WebGPU is here, and it's going to change the web platform forever. WebGPU is a new JavaScript API which is mainly used for 3D rendering, but also GPU-accelerated compute shaders. Today, we're going to explore this new universe by focusing on maximum compute power. Let's talk about functions, because it doesn't matter if you're building a game or a simple website. Functions are the building blocks of any application. The problem is that some of these functions are lagging behind. How do you know which function is slower and which one's fast? One thing you can do is taking a snapshot of time. Then run the function, let it do its thing, and once it's done, do the same thing again. Subtract the first number from the second one, and you get the runtime speed of your function very easily. This method of measuring performance is extremely simple, and because of that, it's also deeply flawed. Think about running a AAA modern game on your computer. On my computer, that game might run at 200 FPS very easily, but it might struggle to even reach 60 FPS on your computer. The same algorithms can run very differently based on the environment. We need a more robust system for measuring performance. A magical box that takes our function and tells us how fast it is without running the algorithm. Computer engineers are smart, so they've already designed the system, and it's called the Big O notation. Big O tells us how the runtime speed of our algorithm grows as the input gets larger. I'm going to explain how this works when we get to the examples. The key in building a robust measurement tool is using both of these methods at the same time. Our goal for today is not only to win the exact speed battle, but also winning in Big O. Let's have a look at example number 1. Let's say that we have 2 arrays of numbers that have the same length. What we're going to do is just sum the numbers of these 2 arrays one by one. To do this, we're going to have a simple loop, and we're going to take the elements of both arrays with the same index, sum them, and store the result in another array. Let's try to implement this algorithm using a WebGPU compute shader. Compute shaders can be extremely fast, and the reason behind their speed is the architecture of the GPU. The GPU is designed to run tasks in parallel. A simple way to think about it is this. CPU programs run sequentially, meaning if each CPU function is a car, this car needs to reach the destination before the next car is allowed to move. A GPU program, however, is like a bunch of cars in a race. All of these cars start moving at the same time, and when all of these cars are done, we're done. And so the cost of calculating many functions is equal to the cost of calculating only one. Now, in my previous video on WebGPU, I left you with a lot of unanswered questions. Now, there's an FAQ Readme file in the description where I answer a lot of the questions you might have right now. Take a look after you watch this video. WebGPU offers 2 pipelines. The first one is the rendering pipeline, allowing you to render 2D and 3D scenes in real time. Watch a previous video in the series to learn more about that pipeline. The second pipeline is called a compute pipeline. This pipeline is going to allow us to run compute shaders on the GPU. But what exactly is a compute shader? A compute shader is an imaginary grid of points. This grid can be 1D, 2D, or 3D. And because we have one-dimensional arrays in our example, we're going to have a one-dimensional compute shader. Each point has its own unique index, and we're going to run a function for each one of these points. We're going to write this main function using WebGPU's shading language, or in short, wgsl. The creators of this language were heavily inspired by Rust's syntax, so you're going to find a lot of similarities there. Now, the input to this main function in our compute shader is going to be the index of the individual points. We're going to run this compute shader for n amount of points. N is the length of our arrays. So the index that we're going to get is going to be from 0 to n. Using this index, we're going to read the data from the first array and also the second array, sum these two numbers, and store the result at the end of the function. Notice how similar the logic is compared to the body of our JavaScript for loop. It's exactly the same, but JavaScript computes the results one at a time when our compute shader does this in parallel. Now, for 10,000 numbers in each array, the JS code is much faster. However, this is where we're going to use big O to see if this is still true for 10 million elements. Whenever you have a for loop that's going through all the elements of an array, the big O runtime is going to be O of n. This means that the runtime speed is going to grow linearly as we increase the amount of inputs. Our WebGPU compute shader, however, is built different. The runtime speed for this compute shader is constant because the only operation that matters here is addition, and every addition is happening at the same time. So in theory, the compute shader is supposed to be faster for large enough inputs. Let's try this. We're going to increase the number of inputs to 50 million. And boom, our compute shader computes the result in the same amount of time as before, and it's about 100 times faster. There's a catch, however. The data that's calculated using the GPU lives in the GPU. Imagine that the GPU and the CPU are two completely separate universes. In order to have data go from one world to another, you need to open an imaginary portal. And that is really expensive. In order to send our two arrays to the GPU, we need to create two GPU buffers. A GPU buffer is an array that lives on the GPU, or at least that's how I think about it. We're going to copy the data from our JavaScript array to this GPU buffer like this. When our compute shader is done computing, we need to send this data back to the CPU. With the cost of this in mind, the speed comparison is going to look like this. And again, we're slower than normal JS. So we've learned an important lesson. JavaScript is probably faster for super simple tasks. The first step is to always optimize your JavaScript code. The second lesson that we learned is to keep GPU data in GPU land. Sending one GPU buffer to different compute shaders is basically free. You can do that without any noticeable extra cost. Or you can somehow display this data using a fragment shader, which is part of the WebGPU's rendering pipeline. But reading the data back to the CPU is very expensive, and you should avoid this most of the times. If you're enjoying this video so far, please give this video a like, because if this video reaches 5,000 likes, you can be sure we're going to make another video on WebGPU. Last time, you guys crushed the like button, and so as promised, I'm here today. Now, let's take the previous example and modify it a bit. Instead of adding the two numbers from the two arrays, let's use them as inputs into a complex math function, Perlin Noise. This function takes the 2D coordinates of a point in space and returns a value between 0 and 1. The image that this algorithm produces looks like this. Now, we can already assume that the WebGPU is going to be faster if we don't return the data to the CPU, because the time it takes to calculate this result is equal to the time it takes to calculate one Perlin Noise function call. But to make things a bit more interesting, let's add another competitor to the mix. JavaScript runs on the CPU, meaning that before we use WebGPU, some alternatives are available. Let me show you the power of WASM. WASM, or WebAssembly, is an alternative language for building web applications. However, we're not going to write WebAssembly by hand. Let's use a superior programming language, Rust. For the past year, I've been seeing the hype around Rust, which is getting bigger and bigger every single day. So let's use it here to see if it lives up to the hype or not. For comparison, we're going to also use my favorite programming language, C++. I know, I'm a weird guy. I'm going to compile Rust using wasm bindgen and C++ using mscripten. Here's my implementation code in JavaScript, Rust, C++, and wgsl. First, I've made sure that the implementation of Perlin Noise is the same across all 4 languages that we're testing. I even wrote the sign function myself to make sure that the underlying math is the same. For 10 million Perlin Noise calls, here's the result. Even though Rust is faster than JavaScript, C++ is the winner in CPU land. Let's compare C++ to WebGPU. Wow, WebGPU is much faster, both with and without reading back the data to the CPU. Now, both of the examples that we've covered so far are basic and not that much useful in real life. So let me show you a really fun example. When I was a kid, I really liked watching a movie called The Maze Runner. Later on, when I rewatched it again, I noticed that I wasn't in love with the movie, but the maze. Mazes have always seemed super cool to me. So let's generate one, procedurally. Here's what we're gonna do. Imagine that we have a 10 by 10 grid of cells. Each cell has 4 walls, and if we manage to destroy the right set of walls, we can generate a beautiful, perfect maze. A perfect maze is a maze that has one and only one solution. The algorithm that we're going to use for the destruction of the walls is called DFS, which stands for Depth First Search. Let's implement this quickly using JavaScript. We're going to start at a random cell and pick a random unvisited neighbor of this cell, hop into it, and destroy the wall in between. We're going to repeat this while we keep track of the cells that we're visiting, so when there's no unvisited cell left from the current cell, we can trace back our steps and try this again. We do this until there's no unvisited cell, and this gives us a perfect 2D maze. I'm going to use my character controller system to navigate the maze and try to find a way out. The runtime speed of this algorithm simply depends on the number of cells because we're going to want to visit every cell at least once. And also, there's an initialization stage for the cells which again depends on the number of cells. This means that the big O runtime of this algorithm is O of n. With that in mind, generating a 1 square kilometer maze is going to take about 400 milliseconds of CPU time using JavaScript. Now, I tried to implement this algorithm in Rust for like 4 days, and I just couldn't do it. Rust is extremely difficult for me to write, and maybe an experienced Rust developer can implement this very quickly, but I moved on because I implemented the C++ version in 30 minutes. C++ performs about 6 times faster than JavaScript, and it gets the job done in about 70 milliseconds of CPU time. Now, WebGPU usually brings us the benefit of having constant runtime speed, so let's implement this in WebGPU. I mean, it would be very nice if we could do that, right? Well, the truth is that we can't. DFS cannot be implemented in parallel. The problem is that tree operations generally involve decision making. And according to the decisions, different branches are going to be taken. You might be thinking there's probably a parallel maze generation algorithm out there, right? And you'd be right. There is. But I'm showing you this example because I'm not going to give you a false sense about what WebGPU can do. If you have to use a certain algorithm in your application and you want to make it fast using compute shaders, you need to sometimes rethink the entire algorithm. And sometimes that's very difficult to do. So lesson number 3 is use C++ for heavy math calculations if you can't use WebGPU. It's usually faster than Rust, and please don't get mad at me. I'm a Rust noob, and maybe I'm not doing things in the most efficient way. But that's kind of the point. This video is not the most fair comparison between C++ and Rust. What I want to show you is what worked for me best in a reasonable amount of time. Now, instead of DFS, let's implement a binary tree. In this algorithm, each cell is independent from the other cells, and you can calculate the existence of the walls independently. You're going to take a cell, randomly choose between the left and bottom walls, and destroy one of them. You're going to do this for all the cells. And that's it. Here's the implementation using a compute shader, and it performs much worse for a maze grid size of 10. But as we know, since this is being calculated in constant time, when we increase the size of the maze to 1000, WebGPU crushes every other language. So lesson number 4 is, sometimes when you have a complex algorithm, it may not be portable to compute shaders. And also sometimes when your input size is not huge, the compute shader is actually going to be slower. And of course, this depends on whether you return the data to the CPU or not, because in this case, we can render the entire maze using the rendering pipeline, and there's no need to return any data to the CPU. A while back, I was trying to learn Unreal Engine for the first time, and within a few days of working with it, I fell in love with this particle system, Niagara. So the thought of creating a particle system really stuck with me, and I know a GPU particle system will probably perform really well. But is there any downside to that compared to a CPU particle system? Let's figure it out. A particle system is all about having this concept of a modifier. A modifier is a function that changes the transform, color, or any other properties of a single particle. Here's a list of all the properties that we care about for each individual particle. I'm going to initialize all the particles positioned like a cube in the middle of my 3D scene. Usually in a particle system, you're going to have different forces affecting the position and velocity of each particle. This is called a force field. First, there's going to be the weight of the particles and the force of gravity. Next, we can add a vortex force, which makes the particles move around the line in a circular pattern, similar to a vortex. Then we can add a point attraction force to draw the particles in closer to a predefined position. And finally, we can add some curl noise on top to make the movement a little bit chaotic and exciting. Now, the main forces that have a good amount of mathematical calculations are these. So these are the ones that I'm going to be implementing in Rust and C++. Let's take a look at the time complexity of this. So for the CPU version of the particle system, we're going to apply all the forces sequentially. So the time complexity is going to be O of n, because the time it takes to calculate these forces for each particle is constant, and the only important component is the number of particles. And for the compute shader, the time complexity is O of 1 again for the same reasons as before. So with that, let me show you the power of compute shaders. For 10,000 particles, the JavaScript version runs at around 12 milliseconds of CPU time, which is deadly for a game. Rust is really slow. It runs at about 15 milliseconds of CPU time, which is even slower than JavaScript. C++, however, is absolutely crushing it. It runs at about 6 milliseconds of CPU time, which is basically a 2x speed improvement. Look, I love Rust's macro system and the fact that it has a very smart way of handling errors, but writing some simple math algorithms is sometimes difficult in Rust, and it's also much slower than C++ in most cases. Now, we all know that this is all a joke. Let's take a look at our compute shader. Our GPU particle system runs at 0.03 milliseconds of GPU time for 10,000 particles. That is a 200x speed improvement compared to C++. And since this is being computed on the GPU, you can also very easily visualize these particles using the WebGPU's rendering pipeline. Use compute shaders for these kinds of algorithms where you can do a lot of the same things at the same time. I didn't really talk about the technical side of WebGPU that much because my goal for today was to show you some exciting ideas without getting into too much detail. You can find some great articles down below which explain how compute shaders work much better. At the beginning of this video, I told you that we're going to make JavaScript 16 million times faster. Well, I actually lied. We can't expect WebGPU to perform miracles. I mean, that's impossible to do. But hopefully, I've inspired you to create something amazing. Because if you take action today, you will be able to inspire countless amounts of people. And in this manner, we can make web applications infinitely faster. That's going to be it for this video, guys. Give it a like if you learned something new, because this took me a long time to make. Check the FAQ Readme file in the description to read the things that I discovered that didn't make it into the video. And also, corrections of any mistakes in this video will be in there, because there's always going to be mistakes. Thank you so much for watching, and I'll see you in the next videos.